Okay, then onward with even more graphs. Something I forgot to mention while we were looking at the last one, which we can see here in Desmos, is the number of turning points. The number of turning points and the degree of the polynomial are closely related. This polynomial has, notice it's nice and smooth and it goes on forever in both directions. It has two turning points, this one and this one. And its degree, we know from our previous work, is 3. The fact is that if a polynomial has degree n, it can have at most n minus 1 turning points. So if we see 2 turning points, we know that the polynomial has degree at least 3. Okay, so back to the script. Example 5. Okay, we have y is equal to x plus 2 squared times x minus 1 times x minus 3. And so we have degree 1, 2, 3, 4. We have 4 linear factors. So it can go up like this on both sides, like a regular parabola with its interesting part here, or here's an interesting part and down on both sides, but it would only do this if it had leading coefficient that was negative, so it's not going to be that, is it? Okay. There. Fresh start. Okay. So here I see I'm going to have a touch and go. Here I'm going to go through. And here I'm going to go through. And my y-intercept at f of 0, I imagine that I have 0 here, so I have 2 times negative 1 times negative 3, in other words, 6. So let's put these points that we know about on the graph. Negative 2, we have a 0 there. Positive 1, positive 3. Okay, and here, point 0, 6. Okay, so because of the even behavior, we can put in the endpoints here, or because it's a polynomial of even degree, we can know what its end behavior is. Okay, we have a touch and go at negative 2. It's got to come from there up, do a touch and go, and then head up for y equals 6. Then back down to do a go through there and a go through there, because positive 1 and positive 3 are zeros of multiplicity 1. And so I connect all the spaces and try to make it nice and round. And there we are. And of course, I'm going to, in principle, know which parts are greater than 0 and less than 0. I'm not going to spell that out right now. What I do want to take note of is the touch and go here because of the degree of 2. So touch and go goes with even degree up there. And the number of turning points, we have 1, 2, 3 turning points So the degree has to be at least 4. And of course we knew it was of degree 4 going in. Okay, so if we can predict the shape of the graph by knowing something about the linear factors, we can go the other way too. Because we have this relationship. If we find a factor of a polynomial, we have just found a 0. And it works the other way around. If we find a 0 on the graph of a polynomial, then we have just found a factor. And this is going to be really important when we try to figure out from the graph of a polynomial what the equation is. When we look at this graph in Desmos, we can see that we have a 0 of multiplicity 2 at x equals negative 2. So this must be, for x plus 2 squared, a 0 of multiplicity 1 at x equals 1, and a 0 of multiplicity 3 at, at multiplicity 1 at x equals 3. Well, that is also the very same polynomial that we were graphing here, with zeros at negative 2, 1, and 3, and a 0 of multiplicity 2 right there. So, was it a shabby graph that we made? Hey, we could do a lot worse. Here's an example where we start with a graph and then try to figure out what the equation is. So, observations. I have 1, 2, 3 turning points. It's pointing down on both sides. It has a 0 here, a different kind of 0 here, and another kind of 0 here. And there, it has that y-intercept. So, am I going to tell you what it is? You can send me a message if you have it to ask if you need me to confirm it for you, or just go to Desmos yourself and fool around with it with the facts that you know, or use your calculator. See if you can make a graph that looks exactly like this. And then when you've finished with that one, try on this one. Now, this graph has something extra in it. And it has to do with this y-intercept. Okay? All of our graphs up to now have had a leading coefficient of 1, or maybe in an extreme case, negative 1. But here I can see what the zeros are. It's a parabola, right? With zeros 1 and 3, so we know what to do with that. But make sure that when you put in x equals 0, that you get out y equals negative 6. Okay? That's the challenge on this one. Now, there's one little old landmine that I didn't mention yet. I did look it up, landmine, today. It said a concealed yet incipient crisis. That landmine is this, that the zeros of a polynomial are not necessarily real numbers. Oh yeah? Well, suppose that this is our polynomial, x squared plus 4. Perfectly legitimate polynomial. However, From our knowledge of transformations, we know that the graph looks like this. It never does intersect the horizontal axis. Yet it does have zeros. If I solve this equation, can I solve that? Can I take the square root of both sides? Can I actually say that plus or minus the square root of -4 is equal to x? I can only if I use my imagination. And imagination is what that little I stands for. We will usually write this 2 times I. Okay, so here's the deal. When you see a turning point, when you have turning points that tell you, for example, that a polynomial has to be of at least degree 3, but you have only one real zero, you must have some complex zeros in there somewhere. If you have no intersections with the real axis at all, then you have no real zeros. This can happen only with an even polynomial. I'll let you think about that one. And so we have to get into complex numbers. We're not going to worry about those at all right now, but I would be derelict if I made no mention of them in this lesson about polynomial basics. Okay? So, I want you definitely to try to figure out those Desmos polynomials. I hope you'll get the same kind of satisfaction I do when you have done it. And we'll be talking about more polynomial stuff again.